The topic of section 4.2 is the mean value theorem, but before we begin talking about it, we're going to look at a special case of it, Rolle's theorem. Alright, so Rolle's theorem down here says that if f is a continuous function on a closed interval and differentiable at an open interval, so that's saying it doesn't need to be differentiable at the endpoints, just needs to be differentiable in the open interval, with the additional condition that f of a is equal to f of b, then there is at least one point C in the interval AB such that, conclusion, f prime of C is equal to 0. Let's take a look at this in this picture here. So we have this function f of x here that is continuous, so it meets condition 1. It's on a closed interval between a and b, so it meets condition 2. And it's differentiable. Now, graphically, I can see that it's differentiable because it is smooth. Remember that anytime that I had a sharp turn, I was not differentiable. That's condition 3, so I can visualize that this is differentiable. And then I have to have f of a equal to f of b. This is the fourth condition. And f of a, that y value, is equal to f of b. And so I meet that fourth condition. Then, what the mean value theorem says is that there exists at least one point between a and b such that the derivative is equal to 0. And the derivative equal to 0 means we have a horizontal tangent. And even more, because we're continuous and differentiable, in a closed interval, it's also guaranteed to be an extrema. So it can be used to identify the existence of extrema. Okay, so here's a candidate C. It's in the interval between a and b, and it satisfies f prime of c equals 0. Now, the Rolle's theorem guarantees the existence of at least one point C, but there happens to be another one over here, C2, that also is going to satisfy. So there could be more than one. This one also has the condition that it's in the interval and its derivative is also 0. So at least one has to exist. Sometimes there's more than one. Alright, so given a function here, g of x, I want to use Rolle's theorem to prove, and we're going to be proving here, so we're going to need to be showing the existence of all the conditions, prove that g prime of x is equal to 0 at some point between the two intercepts, verify the results graphically. So the first thing I need to do is discuss continuity. The easiest way to discuss continuity is to discuss the domain. So let's find the domain of g of x. So the domain of g of x is, I need my x's to be larger than -4 so that I don't get that 0 on the inside. So I'm going to have -4 to infinity. Okay, so I am not continuous everywhere, but the domain is -4 to infinity. Now, it does say, I need a closed interval, I know that, right? And it does say between the two x-intercepts, so I need to find those as well. Okay, so we're doing some prep work before we can do our proof. So the x-intercepts are going to be places where g of x is equal to 0, and that's going to be where x times the square root of x plus 4 equals 0. So x equals 0 or square root of x plus 4 equals 0. So that gives us x plus 4 equals 0 or x equals -4. So the two x-intercepts are 0 and -4. Okay, so that means that we want to have the closed interval between those two x-intercepts. So condition 1, we're trying to prove continuous. So we're going to say, ooh, it's called g of f. But g of x is continuous on, and I need a closed interval, so it's continuous on 0 to negative, well, that wouldn't make sense. Sorry, I was looking at those in order. I need to focus here. Continuous on the interval -4 to 0. Put them in numeric order. not in the order that you found them. So it's continuous on the interval -4 to 0 because it's a subset of the domain. I'm going to restate that again. So instead of saying it's a subset of the domain, I can just say that it's continuous on the interval -4 to 0 because it's continuous on -4 to infinity. So if I rephrase number 1, I think to make it a little easier to write, so just a rephrasing of this. I'm going to say that g of x is continuous on -4 to infinity. That's the domain. Then I can say, therefore, g of x is continuous on -4 to 0. I need to get that closed interval worked in there somehow. Okay, so I've phrased it in 2 ways. We can make a choice, but I have to figure out how to phrase this to make sure that I can guarantee that it's continuous on the closed interval. Since it's not necessarily obvious because it isn't the domain, I need to state that it's continuous on the interval and give a reason. So subset of the domain is one reason, or if I say it's continuous on and give the whole domain, then I can prove that it's continuous on that subset interval. Okay. If you ask me which one of these prefer, I probably prefer the second option for number 1. So I'll give it a star. Okay. Now, when I labeled these before, the closed interval, it's going to loop in with number 1, so we're really going to have 3 conditions to show. I need to show differentiability next. Let me go back and renumber these. These are going to be together. So this is going to be your 2, and this is going to be your 3, because these are going to be together. Okay? So we have 3 things to show. Next, I need to show differentiability. So to show differentiability, I want to find the derivative. Okay? So, for step 2, let's find the derivative. So g prime of x is equal to the square root of x plus 4, because the derivative of x is 1, plus x times 1/2 times x plus 4 to the negative 1/2 times the derivative of the inside, which is 1. So this is square root of x plus 4 plus x over 2 square root of x plus 4. We just move that negative 1/2 down into the bottom. Now, because I have a square root in the denominator, the domain of g prime of x is going to not include the -4, but of everything else. So we're going to make that note. The domain of g prime is parentheses -4 to infinity. Everything else is fine. You can't include the -4 because it's in the denominator now. The square root's in the denominator now. Now, I don't need to find the domain of g prime. I need to find out where regular g is continuous. So we're going to conclude that, therefore, regular g of x is differentiable on the open interval -4 to 0. Okay? So this statement relies on these 2 things. It relies on stating what the domain of the derivative is, and then I can conclude from the derivative. Remember, these 3 dots are therefore. I have a therefore statement up here as well. Therefore is the 3 dots. Okay, this is my therefore. The domain of g of x gives me, therefore, I'm continuous in the closed interval. The domain of g prime of x gives me, therefore, the original function g is differentiable now on the open interval. That's what I needed. And then I need the third condition. And the third condition is that f of a equals f of b. So that's, in this case, g of a and g of b. A and b, remember, are -4 and 0. So g of -4 is equal to C, that's negative 4 times square root of negative 4 plus 4, so that's 0. And g of 0 is 0 times 0 plus 4, so that's 0. So we have another therefore. G of 4 is equal to g of 0. They don't have to both be 0, they can both be 2. They need to be the same, they need to equal each other. Okay, so this is our third condition. The last thing we need to do is write a conclusion. So these are the 3 things that I need to show in order to get a conclusion. So my conclusion is going to be thus. Again, remembering what has to happen here. Thus, there is at least one point C in the interval a to b such that f prime of c is equal to 0. I need to make a statement to that effect. I'm going to use some extra paper here. So thus, okay, there exists a C in the, and it was in the open interval, a to b, so in the open interval, negative 4 to 0, such that f prime of c is equal to 0. That's my conclusion. So I have to have that conclusion. Now, if you prefer to write that fancy, we can write that fancy. So there exists a c in the interval negative 4 to 0 such that f prime of c is equal to 0, says the same thing. Okay. So you can either write all the words out or you can write the symbols, but this says the exact same thing. There exists a c in the interval such that f prime of c is equal to 0. So in order to use Rule's theorem to prove something, you need to assert the 3 conditions and then give the conclusion.